Welcome back to Physics 141 Online. We're now moving from our study of mechanics, which we recently completed by finishing rotational dynamics, into the topic for the rest of the semester, and that is an introduction to thermal physics, or what some books call thermodynamics. The range of topics that we'll cover is broad, but we'll start today by beginning with a discussion of temperature, then what we mean by thermal energy, or transfers of thermal energy in the form of heat, and finally, the ideal gas law. So, temperature and what's called the zeroth law of thermodynamics. A little bit later on in the subject, we will find out microscopically what temperature means and how it's related to the properties of gases and liquids and solids at the microscale. But for now, we'll be satisfied with an operational definition of temperature. And that is that if we bring objects into contact, one cold, one hot, then we observe that the properties of those objects will change. And we now understand that what's happening is a form of energy, thermal energy, is being transferred from the hotter object to the colder object. And if we leave them in contact long enough, eventually the properties of those two objects will stop changing. When they stop changing, those objects are in what's called thermal equilibrium. And we say that those two objects have the same temperature. And we measure their temperature usually with reference to a third object, which gives us formally a way of expressing what's called the zeroth law of thermodynamics. And the zeroth law says that if there are two objects which are each in thermal equilibrium with a third object, then those two objects are also in thermal equilibrium with each other. So if that third object, let's say, is a thermometer or other device that has some kind of a readout on it that allows us to measure the properties of an object that it's touching, we call that reading a temperature. And the temperature is a measure of that object's tendency to either give up or absorb thermal energy when it comes in contact with something else. So the thermometer, then, being that third object, if we have two objects that when you bring them each into contact with a thermometer, they give the same reading, that means that if we bring those two objects into contact with each other, there won't be any flow of energy. So they are also in thermal equilibrium with each other. It seems kind of self-evident, but there is a formal principle involved there. So having talked about these kinds of two objects that are in thermal contact, when these two objects are touching each other or otherwise connected somehow, there is a pathway for thermal energy to be transferred. And just to give you a little bit of an advance notice, thermal energy is related to the kinetic and potential energies of the atoms and molecules that make up those objects. Heat is the common word that we use historically for a transfer of this kind of energy. And one of the things that can happen is that when a hotter object transfers thermal energy to a colder object, the temperatures of the two systems change. However, there's other things that can happen. And so just to make a list of all three possibilities, if thermal energy or heat is transferred from one object to the other, one thing is the temperature of the objects change. There will be a delta T in their temperature. Secondly, there might be a transfer of thermal energy, but temperature doesn't change. Instead, that transfer of thermal energy causes the phase of one of the objects to change. In other words, an ice cube thrown into a cup of coffee. There's a transfer of thermal energy from the hot coffee to the cold ice cube, but initially the temperature of the ice won't change. However, the phase will change. So what was solid ice will become liquid water. And then thirdly, another possibility is that an object could do work on its surroundings. And that is especially important when we think of engines, when we think of a piston and a cylinder of gas, and how that piston can do work on the gas. So when heat is transferred, one of these things is always happening. And for now, we're going to postpone discussing the third one until we talk about heat engines a little bit later on. But we will first focus on 1 and 2. And the kinds of transfers of heat that lead to 1 and 2 they fall within the study of what's called calorimetry. And calorimetry is the study of the heat transfers that take place when two objects initially at different temperatures are brought together, and then they reach a common final temperature, and the study of those kinds of problems is called calorimetry. Q is the symbol that we give to this transfer of thermal energy. It's appropriate for us to say that an object has a certain amount of thermal energy. And so when energy is transferred from that object to something else, we just say that the transfer of thermal energy is called the heat that's transferred. So I just mentioned this because it is actually incorrect to say that an object has more heat than another object. We actually say it's got more thermal energy than another object, and if energy is transferred, then that's called heat. By convention, this Q quantity, which will have a numerical value, can have a positive or a negative sign. So if Q for an object is positive, it means that that object is absorbing heat from something it's in contact with. If Q is less than 0, it means it releases heat. So heat transfer, as we said, one process, is where heat transfer causes a change in the temperature of an object, but the phase stays the same. And experimentally, we can see that the greater the change in the temperature, the greater the amount of thermal energy or heat that's transferred. And there's a proportionality constant in that relationship, which is particular to each material. So in other words, this constant C that we call the heat capacity is different for a piece of copper than it is for a chunk of ice. It's different for aluminum than it is for gold. And so it is a material property. And in the original form in which it's written here, C delta T, since Q is an energy, it's got units of joules. Temperature has units of Kelvin in fundamental units. And so C would have units of joules per Kelvin. The problem with that form of the equation is that C also depends on how big the sample is. So a 1 kilogram sample would have a greater heat capacity than a sample that's 1 milligram. And rather than have that kind of a quantity, we would actually like to define something that is the same for all amounts of the same sample. So if I have a piece of aluminum, lowercase c, which we call the specific heat, is related to uppercase c by being uppercase C divided by the mass of the object. So the so-called specific heat is the heat capacity per unit mass, and you can see that with the equations. So what we will most often use is to write down Q as the mass times the specific heat times the change in temperature. So that is the equation we use when heat transfer causes a change in temperature. But if heat's being transferred to an object and its phase is changing, then we observe experimentally that that change in phase happens while the object stays at a fixed temperature. So until all of the phase change is accomplished, the object does not change temperature. So if a piece of ice is in a warm swimming pool and that ice is melting, the temperature of the ice stays at a fixed temperature until it melts. And after it melts, of course, then it can warm up and eventually reach a final temperature because of the water in the pool, because presumably that water in the pool is at some elevated temperature. But while the phase change is going on, the temperature of the substance that's changing its phase stays fixed. And so the heat that is being absorbed in that process does not produce a temperature change. Instead, it produces a phase change. So for that kind of heat, we write it as the mass of the sample times L, where L is a constant for a particular material that's called the latent heat of transformation. And this is joules per kilogram of sample. So we can measure this experimentally just like we would with the specific heat, and then we can look it up in a table. We can find what the latent heat of transformation of aluminum is, or copper, or gold, or silver, or ice, and that's something that is important to have available if we want to study heat transfer. Here is the important equation at the very bottom of the page that we use to do all calorimetry problems. And it's actually a thermal energy form of the law of conservation of energy. And it goes like this. In an isolated system, and the system is almost always going to be composed of more than one part. There often will be two parts or more parts that are all in thermal contact with each other. But if then that system is isolated from the rest of the universe, so no other heat can get in or leave, in that kind of a special system, the sum of all thermal energy transfers must be zero. And that's because thermal energy is conserved, right? So if I have a cup of coffee and then I put a cube of ice into the liquid, I have a system there that's got three elements. I've got the cup, I've got the liquid, and I've got the ice cube. And if I add up the thermal energy transfers, the heat transfers of each of those three objects, then they should equal zero. And that's an important equation. In this problem, of course, we have to pay attention to signs because each of those objects is going to have a different Q. And if we add all these things up and get zero, the only way that can happen is if some of those Q values are positive and others are negative. So remember, a positive Q means that that substance is absorbing thermal energy. A negative Q means that substance is releasing energy. So make sure to pay attention to signs. Here's an example. We won't work out the numerical values, but we'll set it up. 100 grams of water at 20 degrees C is poured from the tap into a well-insulated container. Well-insulated means that no heat can get in or out of that container from the outside. So it's just the water in the container. A 15-gram aluminum block initially at 90 degrees C is dropped into the water. What's the final state of the system? And that might seem like a curious question, but what it really means is, in the final state, when equilibrium is reached, and we might have to wait a long time for that to happen, but when the properties of the system finally stop changing, what do we have left? Okay, how much water and at what temperature? How much aluminum and at what temperature? So that's the final state of the system. And in systems where there might be changes in phase, that's where it's important to remember that you have to calculate how much of each component there is at the end. So the final state means, again, how much and at what temperature each component is. Now, the identify step in our problem-solving method. We know in this problem there's no changes in phase. Water boils at 100 degrees, and there's no way that the aluminum block at 90 can ever transfer enough heat to make the water go above 100. And also aluminum, it's at 90 degrees C is well below its melting point, so the aluminum block is initially solid. It's just going to get a little colder. It won't heat up. So all we have to do is use the calorimetry equation to solve for the final equilibrium temperature. We don't have to worry about any changes in phase. Then, developing a plan, the aluminum block releases heat because it's hotter than the water, and the water absorbs the heat. So those two terms will be added together to give 0. And this heat transfer is described by the equation, right? That add up all the heat transfers, add up all the thermal energy transfers, and that tells us that the Q released by the aluminum, because it's the hotter object, plus the Q absorbed by the water is equal 0. And if we can put in expressions for those two, they will include the final temperature of the system, and then we can solve for it. So here's how it goes. Q is mc delta T. So the Q of the aluminum is mass of the aluminum times the specific heat of the aluminum times the final temperature of the aluminum minus the initial temperature, TAL sub I. And we always do final minus initial in that equation. And let's think for a minute about this. The final temperature's got to be lower than 90 because the initial temperature was 90, and so this term should be negative, which makes sense. The aluminum is releasing the heat, and a release of heat means a negative Q. The water term, by contrast, should be positive, right? Mass of the water, specific heat of the water, T final minus T water initial. Well, the final temperature of the water is going to be higher than 20 degrees. And so this term in parentheses for the water should be positive. So those two add together to give 0, and the evaluation step with this equation is just to multiply through those two equations, get all the terms that have T final in them, factor out a T final, and solve for it. And that's what we're trying to find. What is the final state of the system? We will say the 100 grams of water and the 15 grams of aluminum are at a final temperature TF. So that will solve the problem. When we're done, we check the units, check the value, and one practical thing that we can do is check to see whether the final temperature is indeed between 20 degrees and 90 degrees. There's no physical way it would make sense for the final temperature to be less than 20, or on the other hand, to be greater than 90. So there are often some ways that you can check your answer to see if it makes sense. Make sure to do that. Here's another example. Okay, and this one involves potentially changes in phase. 100 grams of water, 10 grams of ice are in a well-insulated thermos, initially at 0°C. And one of the things that you'll see in the textbook, it's an experimental observation, and that is that when you have a liquid and a solid form of the same substance that coexist, as in this problem, 100 grams of water and 10 grams of ice, they must coexist at the transition temperature, at the phase change temperature, if they are really in equilibrium. And so that's why together the only way this can happen in equilibrium is if the ice and the water are both at 0 degrees, because that is the melting point for ice. So a 100-gram copper block initially at 90 degrees C is dropped into the mixture. What is the final state of the system? Here, the problem is a little more complicated. We know the final state of the system will still include 100 grams of copper, right? Because the copper is not going to melt. No, and it won't change the amount of copper that we have. The copper will simply cool off from 90 degrees to some final temperature. But what we don't know is how much water and how much ice will remain, because there's at least two possibilities, right? First, all the ice could melt, and then the ice plus water mixture would heat up to some final temperature greater than 0. So if that's the case, we need to find the final temperature T. The other possibility is maybe there's not enough heat from the copper to cause all of the ice to melt, maybe only some of it will melt. And so if only some of the ice will melt, then that would leave some ice and water still coexisting. That would mean the system would still be at T equals 0. All right, so that means the copper and the ice and the water would all end up at T equals 0, and the unknown in that case is not the temperature, but how much of the ice melts, or how much of the ice is left. So it could be one or the other of these possibilities, and up front we don't really know. And so what you have to do is pick whichever one you think is more reasonable, given what the problem statement says, make the assumption that that's the case, solve the problem, and then see if your answer makes sense. All right, so if I decide in this problem that I'm going to solve it by assuming all the ice melts, so when I'm all done I have 110 grams of water at a particular final temperature. If I do that and I solve for that final temperature, what's going to happen? Well, if I was right and that's actually what happens, I will get a T value that makes sense. So it will be some temperature greater than 0. But of course, less than 90. It can't be as high as 90 because the copper, that's where it started out. And the copper is losing some of its energy to transfer it to melt the ice. So the ice and water can't make it all the way back up to 90. But what if I made the assumption that all the ice melts and it turns out I was wrong? Then what will happen is I will end up with a final temperature, for example, that's negative. And that doesn't make any sense. That would tell me that I'd made some kind of a mistake, that I made an assumption that was not really consistent with the situation. So if that happens to me, then I guessed wrong, and I'll have to move on to step 2 and realize, okay, probably that means only some of the ice melts. So then I'll have to find out how much of it melts. So those are the kinds of choices that you have to make in doing calorimetry problems. And I'll just mention too that in your textbook you'll see that the specific heat is listed in a table, which implies that it's a constant value. And the values that are in those tables are representing measurements that were done near room temperature. However, in the real world, we see that as objects heat up or cool down, their specific heat is actually temperature dependent. And this is a little bit hard to see, but what this is a plot of is specific heat plotted versus temperature for a number of substances. So you'll see, for example, iron, Fe. Iron has different phases, but one of the phases of iron that we see plotted here has a rather steep slope compared to the other ones, which means that on the far left of this, that's room temperature, which is right around 300 Kelvin. And so at room temperature, this phase of iron has a specific heat of 25 in these units, but then when you get up to just over 1,000 Kelvin, where it melts, there the value is about 42. And so it's gone from 25 to 42 over a range of several hundred degrees. But if we actually are doing a calculation with iron at those elevated temperatures, we had better take into account that the specific heat is not constant, but actually is linearly dependent on temperature. And you'll see that for many other materials, at least in limited ranges of temperature, that's also the case, that there is a roughly linear relationship. There are some phases, for example, this liquid, I believe it is, for iron, that, or maybe it's a different solid phase of iron at elevated temperatures, but this shows that at least over a region of about 100 degrees, that there is very little change in the specific heat. So it depends on what the substance is made out of and how the atoms inside that substance are bonded together. But I just wanted you to be aware that sometimes you have to take into account the dependence of the specific heat on temperature, and we can do that using calculus. Now, let's close today by just reviewing a subject that you probably are familiar with from previous high school chemistry courses, and that is the ideal gas law. And just to give a little bit of background into how we got this equation, it was not written down on tablets that Moses brought down from the mountain. It was something that was deduced by careful experiments starting by people like Robert Boyle back in the 1600s. And Robert Boyle discovered something that we called Boyle's law. He discovered that for all gases, the product of the pressure and the volume of the gas. So you have a container, and then you have a certain amount of gas inside, and that determines what the pressure of the gas is exerted on the walls of the container. But the product of the pressure and the volume is approximately a constant as long as the sample's temperature doesn't change. And so if you change the volume, let's say you have a balloon, and you can change the volume of the balloon, then that will cause the pressure to change, but it's the product of the two that stays the same. So Boyle discovered that. We call that Boyle's law, and one way to write that down is that P times V is equal to a constant. But even Boyle realized that that constant depended on the temperature. So the product of pressure and volume is something that depends on temperature. And Charles and Guy Lussac, who were chemists, natural scientists at the same time, just a little bit after Boyle's time, they discovered that that constant in Boyle's law, P times V equals a constant, depends on temperature in a linear fashion, as long as temperature is expressed on the absolute scale, which we call the Kelvin scale. So by combining Charles and Guy Lussac's insights into Boyle's law, they could write down an expression that said the product of pressure and volume is equal to some constant C times the temperature. And it was left for others later on to figure out what that constant represented. P, of course, pressure. You might know that pressure is defined to be the force per unit area that something exerts on an object. And so for a gas, the force that the gas molecules exert when they make collisions with a particular surface, like the surface of the container that's containing the gas, that's the pressure. Volume is pretty straightforward. And experimentally, what other people who came later figured out was that this constant C depends on how much of the sample there is. So if you have a small sample with relatively few gas molecules, you have a small C. If you have a sample that's got a lot more gas molecules, then you have a much bigger C. And so the C actually takes into account the number of molecules or atoms that are in the sample. And so the final version of the ideal gas law in its modern form goes like this. Pressure times volume is equal to n, the number of particles, which are either atoms or molecules, times the temperature, and factored in is this constant that we call Boltzmann's constant. Kb has units of 1.38, or has a value of 1.38 times 10 to the minus 23rd joules per Kelvin. And this is one of these fundamental constants of nature. It is the key experimental constant that relates energy, as expressed in joules, to temperature, as expressed in Kelvin. So there's two equivalent forms, though, of this ideal gas law. And the one that we just wrote down on the previous slide was with reference to the number of molecules in the gas. And this is a one that physicists tend to use a lot. Chemists, by contrast, often want to write it down in terms of a smaller number, rather than using the number of molecules, which is really, really large for a microscopic sample, or for a macroscopic sample. Chemists like to express that number as the number of moles of gas. And so lowercase n can be inserted into this equation by just using the fact that lowercase n, the number of moles, is defined as the number of molecules in the sample divided by Avogadro's number. And so this defines a certain unit of gas that's called the mole. So if we solve for capital N, we replace it with lowercase n times Na. Right? Na, you're familiar with that value from high school courses. So we make that substitution. PV then becomes little n times NaKb times temperature. And Na and Kb are two independent constants, but when we multiply them together, they also just form a constant. And capital R is the gas constant, and it's simply the product of Avogadro's number and the Boltzmann constant, and we get the value to 3 decimal places of 8.314 joules per mole Kelvin. So in terms of the number of moles of gas, the original equation PV equals NKT can be rewritten PV equals lowercase n RT. And this lower equation probably is the one that we'll use more often because it relates to how much of the gas is present in the sample. So they're both correct. The top one, if we know something about the number of molecules, we'll use the top one. If, on the other hand, we know how many moles of gas we have in our sample, we'll use the bottom one. So, one last thing. How well does the ideal gas law describe real gases? Because, after all, we call it the ideal gas law. And in that sense, it's pretty clear that it's an approximation. And we find out experimentally, this is kind of cool, if we plot, if we have a sample of gas and we measure its pressure, its volume, the number of moles, and the temperature of the system, all right, if we go back to the ideal gas law, it says, right, that if we take PV over N times T, we should get R as the constant, right? And so that's what's being plotted on this graph, based on experimental data. So the value should be 8.314. And at very, very low pressures, 1 atmosphere is the pressure that we find in the atmosphere around us at sea level. So at very low pressures, then all gases, hydrogen, nitrogen, carbon monoxide, oxygen, all gases converge to approximately that same value if you form the quotient PV over NT. However, as the pressure increases, what happens is the molecules in the gas begin to interact more strongly with each other. And then you get a slightly different answer depending on whether those molecules are hydrogen molecules or nitrogen or CO or O2, because those molecules interact with each other with different strengths. So as the pressure increases, we go further away from the ideal gas behavior. As pressure decreases, then the molecules don't interact with each other very much, because pressure is related to how close together on average those molecules are. And it's a very remarkable thing that there's this universal behavior represented by the ideal gas law. So in high pressure situations, real gases do behave slightly differently. These numbers will deviate a little bit from 8.314. They all follow this very neat ideal behavior in the limit of low pressure. All right, so that's a good introduction. Hopefully that will help you understand the material in this part of the course a little bit better, and I will see you in class.